In this video, we're going to continue our discussion talking about filters by discussing terms such as the cutoff frequency, resonance, and the slope of a filter. So let's get started with that. Okay, let's continue our discussion now and talk about the cutoff frequency. You actually already know a fair amount about the cutoff frequency. We described it in our last tutorial, we just didn't give it a name. So let me show you where the cutoff frequency happens to occur. If we draw our range of human hearing, and we draw, in this case, a high-pass filter, so we're removing the low frequencies. This point right here, where we actually start removing frequencies, that point is our cutoff frequency. And the same holds true whether this is a low-pass filter or a high-pass filter or any combination. So if we have a low-pass filter, again, this is our cutoff frequency, the point at which we're starting to remove high frequencies in this low-pass filter. Same is also true if we turn this into a band-pass filter. So now we're going to remove this material out here as well as the material here to the right. This is still the cutoff frequency. Nearly all synthesizers have the ability to control the cutoff frequency. So they'll give you a knob that you can turn either to the right or to the left, like that. And as you turn it one way or the other, it is moving this cutoff frequency either to the left or to the right, and creating what we call a sweep, or sweeping the cutoff frequency. So as you turn the cutoff knob on your synthesizer, cutoff frequency knob, it's going to move this cutoff frequency point to the left or to the right. So effectively, it will make our band of frequencies move. As this moves, so will these. And it's going to move that whole thing to the left or to the right. So if we sweep it this way, it'll wind up down here. If we sweep it to the right, it'll wind up here somewhere. So that's what we call sweeping the cutoff frequency, and that's a very common effect for synthesizers, sweeping the cutoff frequency. So filter resonance, what is it? By definition, filter resonance is when we add frequencies right at the filter cutoff point, right at the filter cutoff frequency. So if we had a filter like this, removing high frequencies, so filter cutoff, so a low-pass filter, removing the high frequencies, and we added resonance or turned up the resonance knob, what we are going to be doing is adding frequencies right at the filter cutoff. The more resonance we add, the larger a peak we are adding here at the filter cutoff frequency. Something like that. Resonance sometimes is hard to detect because usually the bandwidth of the resonance is fairly limited or narrow. But you can really hear it when you sweep the cutoff frequency. So if you sweep it to the right or to the left, then you really hear this peak up here, this resonance peak. And I'll demonstrate that for you in a minute. So resonance is adding frequencies right at our cutoff frequency, boosting that point. Now some of you may go, well, Todd, that's really similar to EQ. And it is, and that's the reason we've delayed talking about it until now, is because it does have some similarities to what an EQ does, which can boost or reduce frequencies. So that is filter resonance. You can probably guess what the filter slope is, which is the next item we're going to discuss. It is actually the steepness of how quickly our frequencies are being removed. So right here, this information, how steep this is, gives us our slope. So this would be a filter with a low slope, and this would be a filter with a steep slope. In synthesizer terms, we describe a slope, or the pitch of a slope, in terms of how many decibels per octave are we removing. So if we diagram our range of human hearing and we plot a slope of a filter, we can do that quite easily. How many decibels per octave? So let's say we're starting here at the note A that the orchestra tunes to, so we know it's A 440, 440 hertz. Each octave, you remember that we go up, we double, so this is also an A, but it's 880. Then we go to what, 1760, and then I can't remember the math after that. So each octave we go up, or each octave that we drop, we are doubling or halving the frequency. So if we start right here, and this is our cutoff frequency, and we're going to draw a slope, we first need to know how many decibels per octave is that slope. There are some real common slopes, and they are usually in derivatives of 6. So minus 6 dB per octave is a real common slope. Minus 12, minus 18, and minus 24. Those are real common slopes, filter slopes. So we can plot that. If we come over here and we plot roughly, just kind of guesstimating. I know this isn't a very accurate scale, but I'm trying to make it accurate enough so you understand the concept. If we're going to plot a 6 dB per octave slope, we're going to go for 1 octave up, we're going to drop 6 dB. So there's our point. Next octave up, we're going to drop another 6 dB. The next point, another octave up, another 6 dB, another octave, and another 6 dB. So that is the slope of our filter, a 6 decibel per octave filter slope. Now, if we diagram a 24 dB per octave slope, how would that look? Same thing, we can go up 1 octave from our cutoff, and then we're going to drop 24 decibels. So down to right here. Now, if we plot these points, you'll see that the higher decibel per octave slope is a more drastic reduction in the frequencies. This 6 dB per octave slope does not remove as many frequencies. It only removes these. So it doesn't remove as many frequency as our 24 dB per octave slope, which removes these and these. So it's much more drastic slope. So the slope of a filter is described in terms of how many decibels per octave in frequencies are we removing. So that is filter slopes.